Welcome class to Module 1, which covers linear equations, inequalities, and applications. Please make sure as you watch this video, you are completing the guided notes for this section. The first section that we are going to cover is part 1, which will be linear equations in one variable and solving for a single variable. So, friendly reminder, in case we've forgotten over the very long summer, that an equation is a statement that two expressions are equal. It's an equation because it uses an equal sign. And when we solve an equation, what we're doing is we're finding all values of x, when x is a real number, that make that statement a true statement. So for example, if I have x plus 2 is 9, what value of x will make this a true statement? And I'm hoping you're shouting in your head or at the screen 7, and you would be totally correct. And we're going to go over how to solve these in case you didn't see this. We follow some specific rules. We have properties that as long as we follow those rules, we can solve any equation. So the first type of equations we're going to work with in this course are linear equations in one variable. Next module will escalate it to two variables, but right now we're just going to look at one. And they can be written in the form ax plus b equals c, where x is our variable and a, b, and c are real numbers. And the number one thing that has to be true is that my a isn't 0, because if my a was 0, that x would go away, because any number times 0 is always going to be 0. And we also call this a first degree equation because the greatest power on our variable is 1. You could kind of think that there's an imaginary exponent of 1 up there, and we'll discuss exponents and how to work with them more in module 4. So an example of a linear equation would be x plus 1 is 2. I'm sure you're thinking, okay, yeah, x is going to be 1 because 1 plus 1 is 2. So we've got two properties that we can use to solve linear equations in one variable. We have our addition property of equality and our multiplication property of equality. And my addition property says this: if I have real numbers, a, b, and c, such that a and b are equal, if I add the same number, c, to both sides, it's going to remain equivalent. And this also works for subtraction. So if I had 2 equals 2, which of course you're going to say, yeah, Dr. Miller, that's true. And I added 3 to both sides, that would give me 5 equals 5. That's still true. This also works for subtraction. So we could think of it as the addition and subtraction property of equality. So if I had 7 is 7 and I subtracted 3 from both sides, I'd get 4 equals 4. That tracks, right? And I know it looks kind of silly to write two numbers equal to each other, but I'm just wanting us to see where these properties come from. Next, we have the multiplication property of equality, and that says if I have two numbers that are equal, a and b, if I multiply them by the same number, this was supposed to be purple, but if I multiply them by the same number, it's still going to be equivalent. So if I had 2 equals 2, that's a true statement, it holds, and I multiply both sides by 3, I get 6 equals 6, and that works. The same also holds for division, which is, we could think of the opposite of multiplication. So if I had 6 equals 6 and I divide both sides by 2, I get 3 equals 3, and that holds as well. These numbers don't have to be positive. I just chose to use positive numbers at this time. You could use any integer, really. So what are our steps for solving linear equations? Well, our first step is going to be to simplify the expression on each side by combining like terms. We want to get all of our variables together on one side, and we want to get our constant on the other. I typically will be getting my variables on the right-hand side and on the left-hand side and my constants on the right, but that's just me. You could do it either way. Next, you want to isolate your variable. I like to think of it as we like our x's lonely. That's supposed to be a joke, but we want to get our variable, typically x, all by itself. Next, we can always check our answer if you aren't confident in that you did the steps correctly. Check your answer. If it's on an exam or quiz, check your answer. I'd hate for anyone to miss points for a tiny math error. It's a good way to check yourself. So let's go ahead and solve some examples. I know we're ready. We're like, woo, finally math. So in this first example here, I have 5 minus x equals 18, and I want to go ahead and combine like terms. So I'm going to move all my constants to the right-hand side. I'm going to do that by subtracting 5 from both sides. And I'm subtracting 5 because if I have 5 minus 5, that gives me 0. Nothing will be left. So I just have negative x equals 18 minus 5, which is 13. And you don't have to write that 0. I kind of did for clarity, but I think I'm going to erase it real quick. So I've got negative 5. And I also do my problems vertically so I can kind of see my steps. That's a good way to stay organized. That's something you really have to do in math. So now I have negative x equals 13. Well, that x isn't by itself. It's got a negative in front of it. So I can either divide both sides by negative 1 to get rid of that negative 1, or I could multiply both sides by negative 1. I'm going to divide out of habit because a negative divided by a negative is a positive, so I get x is negative 13. For our second example, I have y over 6 is negative 7. I need to get rid of that 6, so I'm going to multiply both sides by 6 in order to get that denominator to cancel. I have y equals negative 42. And if you didn't know how to do that in your head, feel free to use a calculator to check yourself. I have negative 8x equals 26. I want to get this x all by itself. So I'm going to divide both sides by negative 8. I have x equals 26 over negative 8. And I'm hoping something in your head is going, this is a problem. Because we have to simplify all of our fractions. And I'm looking to simplify this. Well, I think, okay, what's the greatest common factor negative 8 and 26 have in common? I think it's 2, and I would be correct. So it's x is 13 over negative 4. For our fourth example, I have negative 9t minus 10 equals 53. And I don't typically love using t as a variable because it looks like a plus sign, but they may do that in some of your homework. So I have negative 9t equals a positive 63. I go ahead and divide both sides by negative 9. I get t equals 7, negative 7. We have to be precise about that. It's going to be negative 7. Yes. I have 4x over 5 is 12. I need to multiply both sides by 5 to get rid of that denominator. We want our x's lonely. I have 4x equals 60. I'm going to go ahead and get that x by itself by dividing by 4. X is 15. Now I have two fractions. So I have 2x over 9 equals 4 over 3. I'm going to go ahead and multiply both sides by 9. So that gives me 2x equals 4 times 9, 9, 18, 27, 36 over 3. Well, 36 divided by 3 is 12. 2x is 12, so I have x equals 6 when I go ahead and divide both sides by 2. In those previous examples, we were only combining the like terms of our constants. That's our number parts. So let's take a look at when we have several occurrences of a variable. So here I have 5x plus 2 equals x minus 6. So I still need to combine my constants. So I could subtract 2 from both sides, get 5x equals x minus 8. But I also need to combine my variables. You can do this in 2 steps or 1 step. I'm going to show it in 2. So I subtract x from both sides. Here I combined my constants and my variables in different steps. That gives me 4x equals negative 8. I divide both sides by 4. And I get x equals negative 2, right? So you can break it up, have 1 step for constants and 1 step for variables, or you could do them both together. Here I have negative 3x plus 2 minus 4 minus x is 6. That's going to give me a negative 4x minus 2 is 6. I went ahead and combined like terms. I add 2 to the other side. Negative 4x equals 8. So x equals negative 2. You can see my level of creativity when I'm coming up with these problems. Didn't mean for them to be the same. So next, we're going to have to remember PEMDAS, our order of operations. We want to take care of parentheses, followed by exponents, multiplication and division from left to right, addition and subtraction from left to right. So here I need to distribute 2 times x and 2 times negative 5. That gives me 2x minus 10 plus 3x equals x plus 6. I have 5x because 2 and 3 is 5. We add our coefficients. Those are those numbers in front of the variable. We subtract 10. I get x plus 6. I subtract x from both sides. I'm going to add 10 to both sides. I'm moving my variables to the left and my constants to the right, and I can do this in one step or two. I'm doing it in one this time because I'd already show you how to do it in two. So I have 4x equals a positive 16 because my negative 10 cancels out and my x cancels out. So I get x equals 4 as my final answer. And if I was nervous, I could go ahead and check that answer. So when working with linear equations, there are 3 types. So there's going to be conditional equations. All the equations we've seen so far have been conditional, meaning they have one solution. So here I could go ahead and distribute 10x plus 30 minus 2 is 7x plus 28. I've got 10x plus 28 equals 7x plus 28. I'm going to subtract 28 from both sides. I'm going to subtract 7x from both sides. I get 3x equals 0, and you might be like, oh no, 0, that's a problem. Well, 0 is a number. It can equal 0. So if I divide both sides by 3, I would find that x equals 0. So x equals 0, that's still one solution. That's conditional. We can have x being 0 because it's a real number. Identity are equations that have infinitely many solutions. So when you solve them, they're going to end up looking like your variable equals itself, which is a true statement, or some number, let's say 6 equals 6, right? That's a true statement. That means that any x value that I substitute into this equation would lead to a true statement. So here I have 5x minus 15 equals 5x minus 3. If I go ahead and distribute, we see I have 5x minus 15 equals 5x minus 15. I could add 15 to both sides. That would give me 5x equals 5x. So I would find that x equals x in this case. If you did it another way, you might also find 0 equals 0. And that's totally okay too, because that's a true statement. Contradictions are equations that have no solutions. So that would be something like when you end up, you get a false statement, no x value is going to lead to a true statement. So you might find 7 equals 10. That is definitely false. That's a bad sign. So for my example here, I have 5x minus 15 equals 5x minus 4. Let me rewrite it over here so we have a little bit more room. I'm going to go ahead and distribute. I have 5x minus 15 equals 5x minus 20. I could go ahead and add 15 to both sides. I could subtract 5x from both sides. That would give me 0 equals negative 5. This is a false statement, so we say there are no solutions. Or you can write this symbol. That's the symbol for the null set. We'll talk about it later on in this module. But that tells me it's no solutions. For infinitely many solutions, I would just write infinitely. But maybe you should spell it correct. Infinitely many solutions. So let's do a couple examples and identify these as conditional, which is one solution, identity, which is infinitely many, or contradiction, which is none. So we've got multiple occurrences of our variable. Let's start by simplifying both the left and right-hand sides. On the left, I'm going to combine like terms. Negative 2x and 5x is 3x. On the right-hand side, I'm going to distribute 3x minus 12 minus 5. I get 3x minus 9 is 3x minus 17. I'm sure some of you may already see what our answer is going to be here. If I subtract 3x from both sides, I get negative 9 is negative 17. That means there is no solution. Because we got a false statement, that means we're going to have no solution. There are no values of x that would make this equation a true statement. Here I have 6x minus 12 equals 6x minus 2. Some of you might already see what's going to happen here. I distribute 6x minus 12. Both of these sides are the same. That's going to give me infinitely many solutions. This is definitely an identity, but let's go ahead and solve this. I'm going to add 12 to both sides. That gives me 6x equals 6x. I could also divide by 6. I get x equals x. That's true, right? For any value of x that I plug in, whether x is negative 4 or 17 or 2/3, I'm going to get a true statement. So this has infinitely many solutions. Also, you could write the infinity symbol if you want. That works for me too. So why do we need equations? Well, we need equations to develop mathematical models, and models are equations that describe a real-world situation. And I'm sure you have seen this in geometry courses, right? When we're finding like the area of a rectangle or a triangle or things like that. Here we have the formula for an area of a triangle. No matter what triangle, if it's maybe an equilateral triangle or a right triangle, right? No matter what, the area can be found by finding area by taking 1/2 the base times the height. That is a model that always holds true. And when I have a model, just like we're able to manipulate our equations in a single variable to solve for x, we can also take a model and solve it for a specific variable, in this case b, using those properties of addition and multiplication. So my goal is to get this b all by itself. So the first thing I'm going to do is I'm going to start by multiplying both sides by 2 to get rid of that 1/2. So I'd have 2a is b over h, not over h, darn it, b times h. And because they're being multiplied together, in order to get them apart, I need to divide by h. So I would have my final answer, if I solved the area of a triangle formula for b, I'd have b equals 2a over h. Let's take a look at a few more mathematical models and solve them for specific variables. So here I have t minus r is s. I need to solve this for r. So my rule of thumb is leave the variable you're trying to solve for alone as much as possible. I'm going to subtract t from both sides. Again, I don't love t as a variable because it looks like a plus sign. So I have negative r equals s minus capital T. Now that r isn't quite by itself, it's got a negative hanging around. I could multiply by -1 or divide by -1. I'm going to go ahead and multiply. I haven't shown that yet. -1 times negative r gives me a positive r, and then I would distribute this negative. So I'd have negative s plus t. So r is negative s plus t. Next, I have 4b over g is n. I want to solve this for b. So I'm trying to leave b alone as I solve this. To get rid of that denominator, the bottom of a fraction is a denominator. I'm going to multiply both sides by g. 4b equals ng. I'm going to divide both sides by 4. b equals ng divided by 4. Final answer. This first example, this is the formula for interest. You may have seen this before. Interest equals principal times rate times time in years. We'll talk about this more later. To solve this for p, I'm going to divide both sides by RT. So I would have I over RT equals P, and yes, you can divide by two variables at once. That's very nice. Our second example is the perimeter equation for a rectangle. We're going to see this quite a bit in word problems. Stay tuned. I want to solve this for L, so I'm going to go ahead and subtract 2W from both sides. P minus 2W is 2L. We got to get that L all by itself. We divide by 2. So I have P minus 2W over 2 is L, or you could rewrite this as 1/2 P minus W is L. Both are equivalent. Our last example is giving you a little taste of stuff we're going to see in Module 2. This is a linear equation in two variables. Its graph is a line. Let's go ahead and solve this for y, putting it in what we'll eventually know to be slope-intercept form. So I'm going to subtract 3x from both sides, again leaving that y alone. Negative 4y is negative 3x plus 12. I divide both sides by negative 4. I get y is negative 3 divided by negative 4. That becomes a positive 3/4 x minus 3. And I didn't convert this to a decimal because we'll eventually see that this is slope, and it means so much more when given to us as a fraction.